Hello there, and the smart person on the internet. We just experienced three very strong solar events. The sun emitted three strong solar flares. The first one peaking at 6:07 p.m. Eastern Standard Time on February 21st, 2024. The second peaking at 1:32 a.m. Eastern Standard Time on February 22nd, and the third at 5:45 p.m. Eastern Standard Time on February 22nd. Solar activity is expected to peak in 2024 as the solar cycle reaches its maximum. A solar cycle is a sequence that causes the flip in the sun's magnetic field every 11 years. As the field changes, there will be fluctuations in the amount of solar activity, and the sunspots on the surface of the giant star will change. But what exactly is a solar flare? Did the solar flare mess up AT&T's cell phone network, causing outages for tens of thousands of customers? Why do solar flares affect us on Earth? Many people were asking these questions today. And some of these people were in Mrs. Yaklick's class at Anderson Creek Academy in Spring Lake, North Carolina. Hello there, random smart kids in Mrs. Yaklick's class. Her students had a lot of questions about solar flares, so she reached out to me to help answer them, and I decided to make a video to spread that knowledge to everyone. So, here we go. We start off with the question that is the focus of this video. What is a solar flare? A solar flare is a sudden, intense burst of energy and radiation emitted from the sun's surface. It is typically associated with the release of magnetic energy stored in the solar atmosphere. These events can release the energy equivalent to millions of nuclear bombs exploding simultaneously. Solar flares can cause a variety of effects, including the emission of X-rays, ultraviolet radiation, and charged particles, such as protons and electrons, into space. The intensity of solar flares can vary. They are classified into different categories, such as B, C, M, and X, based on their X-ray energy output. Today's largest solar flare was rated as an X6, which is extremely powerful. Do solar flares interact with cell towers? On February 22, 2024, tens of thousands of AT&T customers woke up to their cell phone service not working. There also happened to be a solar flare that day. This led many to speculate that the solar flare caused the cell phone outage. But remember, correlation does not equal causation. Solar flares do not directly affect cell phone communications. The primary concern arises from the increased ionization of the Earth's upper atmosphere during intense solar flares. This ionization can lead to changes in the propagation of radio signals, affecting high-frequency communications from the 3 to 30 MHz range. For cell phone towers and other communication systems that rely on ultra-high frequency communications in the 300 MHz to 3 GHz range, the impact of solar flares in this range of the electromagnetic spectrum is generally limited. The Earth's atmosphere absorbs most of the X-rays and extreme ultraviolet radiation emitted during solar flares, preventing direct interference with ground-based communication systems. So no, solar flares do not affect cell phone towers. Why do solar flares affect us on Earth? Solar flares can affect Earth due to the release of energy and charged particles from the sun during these events. Solar flares emit various forms of electromagnetic radiation, including X-rays and ultraviolet radiation. While the Earth's atmosphere absorbs a majority of this radiation, increased ionization in the upper atmosphere during intense solar flares can temporarily impact radio communications, particularly at high frequencies. Solar flares are often associated with the release of charged particles. When these particles are directed towards Earth, they can interact with Earth's magnetic field and ionosphere. This interaction can lead to geomagnetic storms, which can have several effects. Charged particles interacting with Earth's atmosphere can produce colorful displays of light known as auroras, commonly seen near the polar regions. Geomagnetic storms can cause ionospheric disturbances that affect radio wave propagation. Intense geomagnetic storms can induce electric currents in power lines and affect operations of satellites in orbit. Solar flares are sometimes accompanied by coronal mass ejections, which involves the release of massive amount of solar material into space. If a CME is directed towards Earth, it can interact with the Earth's magnetosphere and trigger more significant geomagnetic disturbances. While the impact of solar flares on Earth can be fascinating, they pose challenges to technical systems, including satellites, power grids, and communication networks. Scientists and engineers continually monitor solar activity to better understand these phenomena and develop strategies to mitigate potential effects on technology and infrastructure. Will we have a heat wave because of the solar flare, and how will our weather be affected by the solar flares? No, a heat wave on Earth is not directly caused by solar flares. Solar flares emit electromagnetic radiation and charged particles, but their influence on Earth's climate and weather is minimal compared to other factors. Heat waves on Earth are typically a result of complex interactions within Earth's atmosphere, including factors like high pressure systems, air circulation patterns, and local weather conditions. While solar activity, including solar flares, can have some influence on space weather and communication systems, they are not the direct driver of heat waves or significant weather changes on Earth. Why do solar flares happen? This is a great question. Solar flares occur due to the complex and dynamic nature of the sun's magnetic fields. The sun's magnetic activity is driven by the convective motion of its hot, ionized gases in its outer layers. The sun has a strong, complex magnetic field that is generated by the motion of charged particles in its interior. The interaction between these magnetic fields create regions of concentrated magnetic energy on the solar surface. Solar flares are triggered by a process called magnetic reconnection. This occurs when the magnetic field lines with different orientations come into close proximity and rearrange themselves. This rearrangement releases a tremendous amount of energy stored in the magnetic fields. As the magnetic reconnection occurs, the stored magnetic energy is converted into other forms, such as kinetic energy of particles, thermal energy, and electromagnetic radiation. The energy release is rapid and intense, leading to the emission of high-energy photons. Solar flares are often associated with sunspots, which are cooler and darker areas on the sun's surface caused by intense magnetic activity. These regions with strong magnetic fields are more likely to experience magnetic reconnection events and consequently produce solar flares. Solar activity, including the frequencies of solar flares, follows an approximate 11-year cycle known as the solar cycle. This cycle is characterized by a variation of the number of sunspots and overall solar magnetic activity. Solar flares tend to be more frequent during the period of high solar activity. What are some telescopes NASA uses to observe the sun? NASA employs several telescopes and instruments to observe the sun, each designed for specific observations across different wavelengths of light. The Solar Dynamics Observatory launched in 2010 and is key to NASA's mission dedicated to studying the sun. It observes the sun in multiple wavelengths, including extreme ultraviolet, to understand solar activity, magnetic fields, and solar atmosphere. The Solar and Terrestrial Relations Observatory, also known as STEREO, is a pair of solar observation spacecrafts launched in 2006. These spacecraft provide spectroscopic views of the sun, allowing scientists to study solar phenomena, including coronal mass ejections and solar flares in 3 dimensions. The Interface Region Imaging Spectrograph, or IRIS, was launched in 2013. IRIS is designed to study the sun's interface region, where the photosphere, chronosphere, and corona meet. It focuses on the dynamics and energy transfer process in this critical region of the sun's atmosphere. The Parker Solar Probe launched in 2018 and studied the outer corona of the sun. And because we're talking about the sun, will the sun ever become a black hole? No, the sun will never become a black hole. The sun does not have enough mass to undergo the process of gravitational collapse required to form a black hole. The fate of the star depends on its mass. The sun is classified as a G-type main sequence star and is currently in its phase of life where it fuses hydrogen into helium at its core. As the sun exhausts its hydrogen fuel in the future in about 5 billion years, it will expand into a red giant and eventually expel its outer layers, forming a planetary nebula. The remaining core will shrink and become a dense, Earth-sized object known as a white dwarf. For a star to become a black hole, it generally needs to have a much higher mass than our sun, typically several times the mass of our sun. When such massive stars run out of fuel, their cores undergo a gravitational collapse, forming a black hole. So there you have it. You learned about solar flares, what they are, what causes them, and that they are not the reason for AT&T losing cell service today. Leave a comment down below on a fun fact that you learned in this video. Oh, hey, did you know that comments are good for the YouTube algorithm? If you would like to learn more about upcoming space missions in 2024, click on the video right here. Or if you'd like to learn more about how and why space is expanding, click on the video right here. And always remember, have fun with STEM.